You're watching a Channel 98 NBISD TV production.
Welcome to another episode of Deja Vu. It's Algebra 2. I hope everyone out there had a very restful mathematical spring break, right? What would spring break be without a little break and a little math, right? Mixed together. Well, welcome back to the program. This is lesson 26, and today we're going to be talking about piecewise functions, something very, very important. It's all important, right? But this is very important. Now, to kind of set the stage a little bit, let's look at Chuck Yeager. Y'all know who Chuck Yeager is? Chuck Yeager's the guy, the first guy that is, to fly faster than the speed of sound. He did it on October 14th, 1947. He was flying in an experimental X-1 rocket plane called the Glamorous Glennis. Yeah, the Glamorous Glennis. It was an orange plane, that's all I know. But it was a rocket plane. And he actually was flying at a particular altitude in the atmosphere, and he was clocked at, let me get this right, I want to get this correct, 299.5 meters per second. Now that translates roughly into 670 miles per hour. And he did this at an altitude of 12.8 kilometers, which is about 8 miles up in the air. Now, it just so happens that if Chuck was flying his Glamorous Glennis rocket plane at an altitude that was below about 6.5 miles, traveling at that speed, he would not have broken the sound barrier. In fact, he was traveling about 670 miles per hour when he broke the sound barrier, and the average speed of sound in the atmosphere is 770. So he broke the speed of sound at a rate that was below the average speed of sound through the atmosphere. Now, how was he able to do that? Well, that's because the speed of sound varies throughout the different atmospheres, okay? And there's no single one equation that can actually model the speed of sound through the various altitudes as a function of the altitude. So what we can do, though, is express the speed of sound per the altitude at different intervals based on the height. So different intervals are going to have different equations that model the speed of sound differently. Okay? So although we can't do it with a single function, we can do it with many different pieces for different altitudes. And that's exactly where piecewise functions come in. Whoa! Oh, I didn't even hear that coming. I guess it was the Glamorous Glennis flying faster than the speed of sound. Anyway, let's talk about piecewise functions. Let's get right to the math. I know you're eager to do it. Here we go. Okay, lesson 26, piecewise functions as promised. Now, I just mentioned Chuck Yeager and the Glamorous Glennis. Here he is posing with his X-1 rocket plane. I don't know if this is before or after. His hair doesn't look so messed up, so I'm guessing maybe it's before. But there it is, the Glamorous Glennis. And you can find this actual X-1 rocket plane that he flew in hanging today in the Smithsonian Institute in Washington, D.C. So anyway, let's get to piecewise functions. What are they? Well, a piecewise function is going to be nothing more than a function that has different rules or different equations defined for different non-overlapping values of the independent variable, which is x. Okay? Different parts or different pieces for different intervals. That's where we get the name piecewise function. Okay? What can be modeled using piecewise functions? Well, a lot of different things that vary at different intervals, like movie ticket prices at the theater. It's not a constant price for everybody. It's a function of your age. If you're in a certain age range, your ticket price is set. If you're in a different age range, your ticket price is set. So you can't model it with a single function. That's where a piecewise function comes in. If you look at a triathlete's time, or his overall time as a function of the legs of the race, he's going to be moving at different rates throughout the race. So if you look at the 3 legs of the swimming, biking, and running, you can model those 3 legs of the race by 3 different equations based on his rate, but it will be so dramatically different. He can bike a lot faster than he can swim, for instance. You're going to have it as 3 different intervals. And the non-overlapping time intervals are the time he spends swimming, biking, and running at the end. Okay, so a triathlete's overall time. What else? Well, people that drive heavy vehicles versus people that drive light vehicles when they're crossing certain bridges. Some bridges charge a toll based on the weight of the vehicle, and they have ranges for weights, okay, instead of specifically per weight. They have ranges for prices. So that'd be another thing. that can be modeled by a piecewise function. So let's quickly revisit the movie theater, okay? Many people in here have been to the movies quite often. There's some good ones out there right now. But let's look at this scenario right here. We got a local theater perhaps, and they're charging for their prime time. This is not the matinee. If you're between the ages of 0 and 12, you pay $5 to get in. If you're between the ages of 13 and 54, you pay $9. Woo, that's a lot. If you're 55 or older, the select citizens, you get the select citizen discount. You're down to $6.50. Okay? So if we're trying to write an equation then for the ticket price as a function of age, which we'll call x, we can't do that with a single equation. So here's what we do. We'll define a variable p to be the price as a function of x. So p of x equals. And I color-coded this here. It's going to be $5, $9, and 6.5. So those themselves are going to be pieces, but we need to now define for what values of x, which is our age, are these prices valuable or relevant. Well, for x equals 0 to less than 13, it's going to be $5. Now notice that it says from 0 to 12, it's $5. Why do I have x less than 13? Well, imagine it's the day before your 13th birthday. You're still going to tell them you're 12, right? So you get the cheaper price. So all the way up to 13, but not including 13, you get in for the $5. Now, as soon as you hit 13, notice the equal sign here, you jump up to the $9 level. And that is good all the way through less than 55. Okay, so again, if you're 54 and your birthday's tomorrow, before you're 55, you're probably going to tell them it's your birthday so you get the cheaper price. Maybe not, though, but you're still subject to the $9 rate. So we'll say less than 55. Now, once you hit 55 or greater, you get in for $6.50, which is 6.5 as a decimal. So this right here is, in fact, a piecewise function. If you were to graph this, these are just constants. So those are y values that are constant over an x interval. Those are going to graph as pieces of a horizontal line. Okay? So here's the function. Here's what the graph looks like right here. The graph of a piecewise function is going to have different pieces of the graph changing at the different values of x where our function changed. Our function changes essentially at 13 and at 55. So on the graph, we're going to change at x equals 13 and x equals 55. So notice right here, here's a graph, movie ticket prices, the y values of the price, the x-axis is the age. So right at here at 13, we have an open circle. That means you can go all the way up to 13 but not including 13. As soon as we jump up here, we have a solid dot for age 13. Now this is still a function. It passes the vertical line test because at the point of exchange, we only have a solid dot at one of the points. If they were both filled in, it wouldn't be a function, which means if you're 13 years old, you get to choose. Do you want the cheaper price or the more expensive price? And that just doesn't make sense, right? Who would pick the more expensive price? So it's important for a function that we don't have overlapping intervals. Okay? Now notice when we get to 55, we jump down to the cheaper price, and that's why this is a solid dot. But up here at the $9, we can go all the way up to 55, not including it. So the open dot basically means don't include, and that translates to the strict inequality. And the closed dot is the including value, and that would be the greater than and or equal to, or the less than or equal to, when we actually can equal that value. Okay, so there's a nice little graph that represents a piecewise function. This right here, because it's just horizontal pieces, actually represents a very special type of piecewise function called a step function. And it makes sense if you think about actually, these are platforms or actually stairs. You could step from here, you can step up to there, and you can step down. Okay, but not all piecewise functions are step functions. This just happens to be a special type. Here's another example of a piecewise function, but this one's already explicitly defined for us. We're given g of x is equal to. Now notice, I didn't talk about this before, but notice how we denote the pieces. We use this brace right here, and this brace is only an open brace. But we group together the different pieces by this open brace, and then we put a comma, and you can write the word if x is less than a certain value, or you can just put x is less than. But we do not, by convention, we do not close the brace. So this is kind of the anatomy of your piecewise function. Now the pieces can be listed in any specific order, but typically we like to list it in increasing intervals values of x. So we start small and we go from left to right on the graph. Okay? So let's look at this function right here. It's g of x, so g is the name, and it's defined by two different pieces. It's part 3x plus 4, which is a line, And it's going to be a line to the left of x equals negative 2. And then it's x squared minus 3, which is part parabola. And it's going to be part parabola to the right of negative 2 and at negative 2. So if you remember the mythological creature called the centaur. The centaur was part horse, part man. And it changed from horse to man at the torso. Below the torso it was a horse. Above the torso it was a man. This is like a centaur, right? It's part line to the left of negative 2 and part parabola to the right of negative 2. So this is like a mythological mathematical creature. Okay? Now what we want to do is we want to graph g of x. And once we have a graph, we'll evaluate at these three values. So here is one way to graph a piecewise function. Notice that the point of exchange, x equals negative 2, is really the most important point on this graph. That's where it's changing from line to parabola. So when I'm sketching these things, what I like to do is I like to actually draw that point first, that x coordinate. So here's a graph. I'll just draw an x and y coordinate. And what do we have? X equals negative 2. So negative 1, negative 2, right there. Now, I like to sketch it from left to right. So we need 2 points for a line. One point that we could use is negative 2. Even though there's no equal sign there, we can use the point as long as we put it with an open circle. So let's plug in a negative 2. 3 times negative 2 is negative 6. Negative 6 plus 4 is negative 2. So at the point negative 2, I have negative 2, negative 2. And it's an open circle because it's less than negative 2. It's not less than or equal to. Well, I need one more point for the line, and I'll get one more to the left of negative 2, like negative 3. Negative 3 is going to be graphed right there at x equals negative 3. Plugging it in, you get negative 9 plus 5 is negative 5. So that's 1, 2, 3, 4, 5. Now this one, I can put a dot on because it's going to be this line everywhere to the left of negative 2. Well, I can use the open circle and the closed dot for my 2 points for a line, and I'll just sketch it going down to the left, okay, with an arrow. It goes on forever. Now, at negative 2, it changes into x squared minus 3. So I want to see where it first picks up. So I'll plug in a negative 2 to the other piece. Negative 2 squared is 4. 4 minus 3 is 1. So at negative 2, the y value of the parabola is 1. And in this case, I can put a solid dot there because it says equal to. So not equal to, I can plot the point, but I'll plot it as an open circle. Equal to, I plot the point as a closed dot. Now x squared minus 3, we know what that looks like. It's a parabola whose vertex is scooted down 3 units. So I can put another point there. And by symmetry now, I'm going to have another point at 2, 1. And that should give me enough points to connect my dots now. So the parabola comes down, hits the vertex, and then it goes up forever. So this is part line, part parabola. It's still a single function. Notice it passes the vertical line test. The only point where it might not is right there at the point of exchange. But in the equation, I'm only giving the y value to one of them, in this case the bottom piece, and the graph I represent that by a solid dot and an open circle. So think of this as kind of almost like a relay race where you've got the line running the first leg of the relay, and at x equals negative 2, he's handing off the baton to the parabola man. Now in this case, I wouldn't recommend this as a good relay because they're not meeting up at the same place. So this guy's going to have to throw the baton to that guy. Okay, but that's another analogy, maybe not a good one, but it is one that might help you think about what's going on here. The different functions are running their races from left to right over their respective intervals, and they can't overlap or it wouldn't be a function. Okay, now let's use this function to evaluate g of negative 3. How do we evaluate g of negative 3? Well, typically we plug it in, but notice I have 2 different pieces, so I have to know which piece I'm using. This says use the top piece everywhere to the left of negative 2. Well, negative 3 is to the left of negative 2, so I plug it in. Negative 3 is negative 9, plus 4 is negative 5. And I've already evaluated that. I evaluated that right here. What about g of negative 2? Now g of negative 2, that's the point of exchange. Do I plug it into both? Or which one? Neither? Well, that's where the equal sign comes in. It says when x is greater than or equal to negative 2, use the bottom piece. So negative 2 squared is 4 minus 3 is 1. And then the next one, what is g of 1? Well, 1 is to the right of negative 2, and we're using the bottom piece for every value to the right of negative 2, so I can plug it into the bottom piece. 1 squared is 1, minus 3 is negative 2. And that's how you evaluate a piecewise function. You have to plug it in to the correct piece over which the interval is defined. Okay? Piecewise function. They take a little bit of practice. All right, let's take a real quick commercial break, watch these public service announcements, but do not go away because I'll be right back here waiting for you. While you're gone, think about this, though. Why did Cinderella's soccer coach always keep her on the bench? The answer when you get back.
I smoked weed and nobody died. I didn't get into a car accident. I didn't OD on heroin the next day. Nothing happened. We sat on Pete's couch for 11 hours. Now what's going to happen on Pete's couch? Nothing. You have a better shot at dying out there in the real world. Driving hard to the rim, ice skating with a girl. Now you want to keep yourself alive? You go over to Pete, sit on his couch till you're 86. Safest thing in the world. Me? I'll take my chances out there. Call me reckless.
The odds of a child being struck by lightning? 1 in 600,000.
Okay, that's it. You're done. Let's go.
The odds of a child being diagnosed with autism? 1 in 150. You know the odds of autism. Now learn the signs. Go to autismspeaks.org.
Welcome back to Deja Vu. It's Algebra 2. I'm your host, Kevin Corpy, talking to you today about Piecewise Functions, Lesson 26. Now, if you think about why Cinderella's soccer coach always kept her on the bench, doesn't sound fair, right? Well, it's because Cinderella, she ran away from the ball. Let's get back to the math. All right, let's look at another example of a piecewise function. This one, though, we're calling m of x, not monster of x, but just m of x, and it's made up of 3 pieces. So it's going to be a parabola, x squared minus 3 to the left of 0, a line between 0 and 4 and at 0, and then it's going to be another parabola to the right of 4. 3 different pieces, so 3 different relays, points of exchange. We're exchanging the baton in this relay race at 0 and then at 4. So 2 points of exchange for 3 different runners. Got it? All right, so how are we going to sketch this graph? Well, I always like to sketch from left to right, but the first thing I do is I get my most important values of x on my graph, which are the points of exchange, x equals 0 and x equals 4. Well, x equals 0 is right here, and x equals 4, 1, 2, 3, 4 is right there. And I only mark those, so you don't have to number them. Now let's go ahead and sketch x squared minus 3. To the left of 0, we know what that function looks like. We just sketched it. So that's going to be moved down here to negative 3. That's where the vertex is. It's strictly less than 0, so I have to put an open circle, not a closed circle. And now I'll draw that parabola coming down, approaching there. So I'm going to take some liberties here and not actually put the points, but it's the same graph we just did on the last example. But it's a parabola, and if I was to continue on, I would continue up on the other side. But I have to stop at 0 because it's not defined to the right of 0, nor is it at 0, open circle. Now, it's going to look like this line between 0 and 4. It's like the middleman. Well, it's a line. I need 2 points for a line. The 2 most convenient points are the starting point 0 and the ending point 4. I put a solid dot at 0 because it's equal, and an open circle at 4. Plug in a 0 and you get 0 minus 3. That's negative 3. Well, that happens to be the same value that we had right here. So it's actually, this is a good baton exchange. They are meeting up at the exact same value. So I drew it as an open circle for the top piece, but I get to fill it in now for the middle piece. And I plug in a 4. 4 halves is 2 minus 3 is negative 1. So that's going to be here, and that's an open circle because it's strictly less than. Now I'll connect those 2 dots with a straight line. So it went from parabola, nice exchange, they share the y value at 0, and then it's going to be a line up to 4. And then I need the next piece. Plug in a 4, and you get 4 minus 4 is 0 squared, which is 0. Minus 2 is negative 2. So notice this last piece, it does not meet up. It starts down here, and that's where the equal, or that's where the equal sign is, so that's where I'll put a solid dot. Now, notice this is also a parabola, and it's in transformation mode. The vertex is moved to the right 4 and down 2. Well, right 4 and down 2, this is the vertex. It's a parabola opening up, so I can just kind of sketch another parabola going off that direction. So this is what the piecewise function looks like. It's connected at the first point of exchange. At the second point of exchange, it's not. We get a closed circle for the bottom piece, because that's where it's equal to, and for the line, we put an open circle because it's strictly less than. Okay, so open circles and closed circles are directly related to the inequalities in the equation. Very important you practice that and get it right. All right, so in the last 2 cases, we had an equation and we graphed the function based on the equation. Let's try to go backwards now. we actually have a piecewise function graph. We want to write the equation. Ooh, okay, that sounds fun. We get to create something. All right, well, to do that, notice that this graph is made up entirely of straight line segments, which is a little bit easier to work with because all we have to do is write equations of lines. So notice that the trade is at -4. It goes from slanted line to horizontal line at 4. It goes from horizontal line to slanted line at 4 on the other side. So -4 and 4 are the points of exchanges. The first thing I need to do is write an equation for each piece. And I have these pieces marked. So to write the equation of a line, remember we need a slope and a point. Well, let me go ahead and find the slope of this little piece right here first. So the slope is going to be the change in the y's, which is -7 minus -3, change in y's, over -6 minus -4. Okay, change in the y's, change in the x's. And what does that give me? That gives me -4 over 6 minus 4, -2, which is 2. That's reasonable. This graph rises 2, runs 1, up 2 over 1 to the right. Now, to write the equation of that piece, I'll use the point-slope formula, which is y minus a y value, and I could choose either one. So I'll choose y minus -3 equals my slope times x minus the x value, which is x minus -4. Watch those negatives. Okay? Now what do I do? Well, I will simplify. So I get y plus 3 equals 2x, that's x plus 4, so I get x plus 8. Well, now what I'll do is I'll subtract 3 from both sides, and I get y equals 2x plus 8 minus 3 is 5. So this is the equation of that line, which would continue on to infinity. But I'm going to restrict it to be strictly to the left of -4. Now, look at this piece here. This is a horizontal line. Those are easy. That's going to be of the form y equals whatever the y value is, which is 3. So that's a constant function. Now for this one over here, we can find the equation of that line in much the same manner as we previously did. However, it's going to be over here. We're going to restrict it to go from 4 to infinity. And it doesn't look like it's quite as steep as this piece, so the slope should be less steep. And I'm going to save you the boredom of doing that calculation. But we use the point slope formula, and we get 1/2 x plus 4. Now that we have all three pieces, we can put them together. And here's how we're going to do that. We have to give this function a name. Piecewise function or centaur. Let's call it the centaur function. So maybe c of x. You can get creative with your names if it doesn't tell you to call it f of x. Well, I'm going to put that fancy brace right there. And I like to list my functions from left to right. So my first piece was 2x plus 5. My next piece was the constant 3. And my final piece was 1/2 x plus 4. Now, I have to decide where I'm going to use these functions. I can't use them over their entire domain because we'll have overlapping intervals. So comma, the first one I use strictly to the left of -4 because it's an open circle. So I say less than -4. The next one, notice it's solid dot, solid dot. So it's going to be in between -4 and 4. So we do that by putting x in the middle. We're putting less than or equal to on both sides, -4 to 4. And then finally the last piece, 1/2 x plus 4, is going to be strictly to the right of 4 because it's an open circle. So I'll put x is greater than 4. And if you do that, in little pieces, you can write the equation of the piecewise function. Write the equations of the pieces first, then drop them in there and come back at the end and specify the intervals over which they're defined. Again, takes a little bit of practice. Well, now it's time for my favorite part of the program called
Deja Review.
For Deja Review today, we're going to review the piecewise functions, but we're going to do it in different contexts. We're going to look at the absolute value of x right there. Now, most of you all realize that the absolute value of x function is absolute value of x. You got the vertical parallel lines trapping in the x. And the graph you're probably familiar with too as well. It's the V graph, the V for victory graph. But as you go into higher level mathematics, this absolute value of x might not be the most useful version of the equation. We can define the absolute value of x as a piecewise function. Okay? This is going to be one piece. It's a negative sloping line, and a positive sloping line is going to be the other piece. You don't really even have to know the equations of these lines in order to write the piecewise, so long as you know what the absolute value function does. So let's do that. I've already set up f of x equals, and I've got my brace for my piecewise. Now let's think about the two cases. When we're taking the absolute value of a number, we want it to end up being positive because it's the distance from some point, the center. And distances are always positive. So what if the thing inside the absolute values was already positive? How do you make positive numbers positive? You don't. You take them as they are. So the absolute value of x, we're going to say, is just x itself when, comma. Now for what values of x is x already positive? Well, if x is greater than 0, x is positive. But what about 0 itself? The absolute value of 0 is 0. So we can actually put greater than or equal to 0. But what's the other case? The other case is when x is less than 0. That's when it's negative. How do we make negative numbers positive? Do we just erase the negative? Well, we can't erase the negative in here. So what operation can we do to make a negative number positive? We can multiply it by -1, or take the opposite of it. So if x is negative, we will take the opposite of x. That's what the negative means, the opposite of x. For instance, if x is -5, then this piecewise function says x is less than 0, -5 is less than 0, so it becomes -1 times -5, which is +5. Sometimes students kind of get hung up on this because you're like, if the absolute value is negative, or always supposed to be positive, why do you have a negative right here? Well, I have a negative to make it positive when it starts off less than 0, when it starts off negative. This is the piecewise definition. Now, if you were to graph this, notice the graph y equals x is just our 45-degree line starting at 0. And the graph y equals -x is the 45-degree sloping line in the negative direction, and they do meet up at 0. So there's a nice baton exchange here. So this is a very useful version of the absolute value of x in some cases as you climb the ladder in your mathematical career. There's actually another one as well, but I'm going to save that and give that to you maybe on a later show. All right, we're about out of time, as all good things must come to an end. So lesson 26 is in the books. Piecewise functions lesson is closed. Now, piecewise functions are very, very important. They take a little bit of practice to graph, but once you do, you will be an expert at them, hopefully, and you'll be able to model different things in the real world that vary at different values of x very appropriately. But just remember this, a piecewise function is nothing more than kind of like the mythical centaur, part horse, part man, and it changes at the torso. Okay? That's all a piecewise function is. It's part one graph, part another graph, and it changes at a specific value of x. So if you think about the centaur analogy there, hopefully that'll keep it all into perspective for you and won't seem so scary, although some centaurs can be kind of scary. Anyway, bad analogy, perhaps. That's just my cue to leave, okay? Join me next time, but until then, I am Kevin Corpy reminding you to do your homework.